Unshielded twisted pair cables. Most of us have seen them and used them by now, but how do they actually work? And if they're unshielded, how exactly do they deal with electromagnetic interference? Let's find out. Hello everyone, Darren from i-LAN Technology. Welcome to i-LAN Technology's Introduction to Structured Cabling Principles and DINTEK Cabling Systems. This is the final part of our 4-part webinar series to give everyone a bit more information about the cabling industry and how DINTEK products fit into it. Today we'll be looking at the final subsystems of commercial structured cabling, horizontal cabling and work area components, and we'll also be looking at UTP cabling. Okay, let's get the ball rolling with a look at horizontal cabling. In our previous webinars we went through the structured cabling subsystems under the ANSI TIA 568.1-D standard in a multi-floor building, which are number 1, the entrance facilities on the middle right hand side. Then clockwise we have our equipment room at number 2 and the telecommunications room at number 3. Between each floor is the backbone cabling shown at number 4 top right, which we went through in detail in our last webinar. At the end of the line we have our horizontal cabling on each floor shown at the top left at number 5, and then the work area components at number 6 below it. Horizontal cabling is our 5th subsystem and is defined as the cabling used to distribute out from the telecommunications rooms to the wall sockets at the workstations. It's usually UTP cable but can be optic fibre in some cases depending on the customer's requirements and budget. Referring to the ANSI TIA 568.0-D standard covering generic cabling, horizontal cabling is the cables between our floor distributors and our telecommunications outlets. It can contain a consolidation point in some circumstances, that's the CP just to the right of the arrow, such as if the last section of horizontal cabling is susceptible to damage and needs to be replaced regularly, or if the telecommunications outlets might need to move around a lot. A consolidation point is not an active device like a patch panel, but rather a passive device like a termination block. There's various standards that apply to horizontal cabling, one of which is that it shall be configured in star topology. That means everything goes back to a central point where we have a patch panel and a switch. We don't use point to point like an electrician did to a customer of mine on a pre-wire I was called out to look at back in the mid-2000s. We used to see a fair bit of that back then. No section of conduit can be longer than 30 metres or contain more than 2 90-degree bends between pull points or pull boxes. The reason for that is it'll then require too much force to pull the cable through it, which can damage the cable and reduce its performance capabilities. The length of cable between the outlet or wall plate and the horizontal cross connect, that's the patch panel at the floor distributor, shall not exceed 90 metres. The maximum channel length from workstation to switch shall not exceed 100 metres. Channel length includes the patch cables at both ends. EMI, electromagnetic interference, and clearance from power cables should be considered. In this picture here, the cable has run the data cable right next to a power cable, even sharing the same hole through the nogging. While UTP cable can cope with this sort of thing reasonably well, it would have been better to run the cable on the other side of the next stud, or perhaps put it in conduit. Here's another dodgy example. We have UTP and power cable here side by side without any separation inside the wall plate. On to work area components. The work area components are the wall plates and patch leads connecting the computers, phones, network printers and so on into the telecommunications outlets. Back to our ANSI TIA 568.0-D standard diagram, the work area components are the last leg of the journey in between our workstations and the telecommunications outlets. And now for a look at UTP cables. UTP stands for Unshielded Twisted Pair. Twisted pair cabling is a form of wiring in which 2 conductors, that's wires, are wound together for the purposes of cancelling out EMI from external sources. EMI stands for electromagnetic interference in this case, not a defunct record label. Adding twists to the cable was invented by Alexander Graham Bell way back in 1881, and UTP is now used for most modern Ethernet networks and telephone communications around the world. Basically, a pair of wires forms a circuit that can transmit data. The pairs are twisted to provide protection against EMI as well as crosstalk, which is noise generated by adjacent pairs. Back to the 1880s, with the earliest telephones and telegraph lines, when electric trams were installed in many cities, they started getting noise into these circuits. This caused the telephone companies to convert to balanced circuits, which had the incidental benefit of decreasing attenuation, which increased range, so everyone was happy. But within a few years, the growing use of electricity again brought an increase in interference, so engineers went back to the drawing board and devised a method called wire transposition, which utilised a form of signalling known as differential mode to cancel out the interference. In wire transposition, the wires swapped sides every few poles. This represented an early implementation of twisting with a twist rate of about 4 twists per kilometre, and apparently there's still some of these poles still standing in some rural areas today. So why is it twisted? In a balanced line, the two wires carry equal but opposite signals, and the destination detects the difference between the two as a measure of voltage. Be aware that voltage is not a unit of energy as such, but rather a measure of the difference in electrical potential between two parts of a circuit. The bigger the difference, the bigger the voltage. In our diagram here, let's assume the top line has -2 volts and the bottom line is +2 volts, which makes it a balanced circuit, and the potential difference in voltage is 4 volts. For data transmission, we want the input voltage to be equal to the output voltage. So if we put 4 volts in, we want to see 4 volts out. However, in an untwisted pair, if there's power cables or other data cables nearby, we'll start getting electromagnetic induction on the wires. So we could be continually adding voltage, particularly to the wire closest to the source of EMI, as we move along. In our example here, we have a 220 volt AC line running beside our data cable, and we've been picking up an extra volt here and there along the length of the cable, so now our 4 volts at the transmission end has increased to 8 volts at the receiving end. This causes data rejection and retransmission and slows down the network. But if we add twists to the wires, what happens is we get a reversal of the polarity and therefore a reversal of the induced voltage with each twist. So it's continually adding and dropping voltage as we move along, so the resulting voltage at the receiving end ends up the same as the input voltage we started with, or at least close enough to it so the receiving equipment can decipher it and discard any excess noise. This is called differential mode. To explain this a little bit further, here's an animation of this slide. Let's assume we start out with a balanced line of -2 volts and +2 volts, giving us a total potential of 4 volts. Let's also assume we have a 220 volt AC line running parallel to our data cable, and we're picking up 1 volt of EMI from it with every twist. On our first twist, our blue line closest to the EMI source picks up a volt and becomes 3 volts, and our red line remains unchanged at -2 volts. So we've effectively gained a volt in potential, now giving us 5 volts. But with our twist, now our red line is closest to the EMI source, and it picks up a volt, changing our -2 volts to -1 volt. Our blue line remains unchanged at 3 volts, so we've effectively lost 1 volt of potential and we're back to 4 volts. And so it continues down the line, with each twist gaining and losing a volt in potential each time, so we end up back to 4 volts at our receiving end. And that is differential mode in action. By comparison, in an unbalanced circuit like coaxial cable, we deal with EMI and noise a little differently. Here all of our example 4 volt signal is carried by the centre core of the coax with respect to the grounded screen on the outside, which makes it an unbalanced circuit. If 1 volt of noise is introduced, it adds to the signal being transmitted, making 5 volts, which could interfere with our data. The solution in this case is with the addition of a device called a balun. The name balun is derived from their function of converting between balanced and unbalanced transmission modes, hence balun, such as when converting between coax and UTP. Baluns are available as either current type or voltage type, and in different impedance ratios to suit different applications. Now on to colour coding. It takes a pair of wires to make a circuit, but how do we tell them apart if we want to put multiple pairs of wires in one cable? The solution is we colour code them. The colour code we came up with uses 5 different colours for the B legs: blue, orange, green, brown and grey, which a lot of people call slate. That blue, orange, green, brown, grey pattern repeats every 5 pairs, but the A leg only changes colour every 5th pair. The A legs in the first 5 pairs are white, then red for the next 5, then black, then yellow and violet right up to 25 pairs. In a 4-pair cable, when it was first introduced, we used the first 4 pairs of that 25-pair example. Originally, the blue pair was reserved for voice, the orange and green pairs for data, and brown was a spare which we later used for PoE and then for gigabit and above Ethernet. The reason we reserved the blue and white for voice was that prior to 4-pair cable, voice had its own cable which had a blue and white pair connected to the centre 2 pins of the BT or RJ11 style plug. Data went over a different type of cable. To combine both voice and data into one cable, the RJ45 plug was born, which is similar but wider than an RJ11 plug to work with 4 pairs instead of just 2. RJ stands for registered jack and 45 is just the number we got to. For the sake of backwards compatibility with phones and the RJ11 plug, we kept the voice pair in the centre of the plug on pins 4 and 5, and data went to pins 1, 2, 3 and 6. That's why you can plug an RJ11 plug for a phone into an RJ45 socket and it still works. Our spare white, brown and brown pair went to pins 7 and 8. For pinouts for wiring up an RJ45 plug, there's 2 wiring standards that can be used under the ANSI TIA 568 standard, T568A and T568B. The difference between the two is that pairs 2 and 3 are reversed. That is, the green pair and the orange pair are swapped around, as you can see in this diagram. In Australia we use T568A. Now, while it is true that it will still work fine as long as you stick to the same pattern at both ends, that is either T568A or T568B, problems arise when other cablers come onto the same site, so it's highly recommended that we always stick with T568A. If you use T568A at one end and T568B at the other, you end up with a crossover cable. Crossover cables used to be necessary back in the day when connecting a PC directly to another PC and you didn't have access to a hub or switch, or if you needed to connect hubs or switches together that didn't have uplink ports. These days it's hard to find a network adapter or switch that doesn't have auto switching ports, also known as auto MDI, MDI-X or universal cable recognition depending on the manufacturer. These detect the type of cable and perform a crossover automatically if one's needed. The orange and green pair were initially utilised for duplex 10BASE-T and 10100 fast Ethernet. Duplex means we can send and receive at the same time in that we send on one pair and receive on the other. A crossover is basically connecting the send at one end to receive at the other and vice versa. A simplex signal, on the other hand, only goes in one direction, while half duplex can go in both directions but not at the same time. An example of a half duplex is a walkie-talkie, where you need to push a button to talk and then signal when you're finished talking by saying over, so the other person can then push their button and reply. For gigabit and above speeds over UTP these days we use all 4 pairs. Be aware also that solid and stranded cables require different types of RJ45 plugs. The solid cable type has split pins in order to pierce the insulation and make contact with the wire inside, while the stranded cable type has a solid pin which pierces through the centre of the cable core. Using a stranded cable plug on solid core cable will quite often cut through the whole copper core, causing faults, or if the cable survives the initial crimp, it'll probably eventually break anyway as it gets moved around. This table shows the classes and categories of UTP cables. The left-hand column is the ISO IEC 11801 standard, while the second column is the TIA 568D name that we more commonly use here in Australia. The transmission frequency rating for each category of cable in the third column is a measurement of the number of cycles, that is waves per second, called hertz. 1 hertz is 1 cycle per second. That's the range of frequency the cable has been designed to support under the standards for 100 metres without losing too much signal. The final 2 columns are about bandwidth in bits per second for each category. The transmission frequency rating of the cable is just one of the criteria the cable needs to achieve to meet that standard for its class or category, and transmission frequency doesn't necessarily play a role in its bitrate performance. The standards specify qualities for each category of cable like wire gauge and composition and how it needs to be constructed to handle impeding factors like EMI, echo cancellation, equalisation, DC balancing, near-end crosstalk, far-end crosstalk and so on, and that's with our twist rates, wire spaces, screening and shielding and so on. All of these factors combined give us the cable's performance. What that means is we may very well be able to achieve some very respectable bit rates over lower rated cables, but we won't necessarily achieve it over the same distance due to the lower standards of the cable. For example, Cat6a can support 10 gigabits a second over 100 metres under its standard, but if we try 10 gigabits a second over Cat6, which only has to support 500 MHz up to 55 metres under its standard, we might only get 30 or 50 metres or so, depending on other external impeding factors like crosstalk and EMI and so on, and other factors that affect SNR. If we try to transmit data at 10 gigabits a second over Cat5e cable, we might only get 20 or 30 metres. Beyond that, the speed will drop off sharply. The take-home message is that if you want 10 gigabits a second over 100 metres, you go for Cat6a cable, but if your cable runs are under 50 metres, you can get away with Cat6. If you're only using gigabit NICs and switches anyway, then Cat5e will still do the job just fine. But with that being said, Cat6 will still do it better, and since the price between cable categories is relatively small these days anyway, you may as well go up a category or two and future-proof yourself a bit as well. Cat7a and Cat8 will perform better than Cat6a, but not by much. These cables require stringent grounding and installation practices for data speeds up to 40 gigabits a second, but even then we're only talking 30 to 50 meters, or possibly 100 gigabits a second up to maybe 15 meters. These cables are designed for higher throughput, up to 40 gigabits a second over shorter distances, with reliability and throughput guarantees for the likes of data centers, corporations and large organisations and so on, rather than for general office cabling. This table shows common industry abbreviations for UTP cable with different levels of screening and shielding. Screening and shielding are enhancements we can add to the cable to reduce impeding factors and increase range or signal quality. Looking at the ISO IEC 11801 names in the second column, the code before the slash designates the screening for the cable itself, while the code immediately after the slash determines the shielding for the individual pairs. U is unshielded, F is foil shielding, S is braided shielding for the outer layer only, and TP stands for twisted pair. For example, U/UTP on the top line there means the outer sheath is unshielded and the individual pairs inside are also unshielded. Unshielded twisted pairs sounds a bit strange though, so we usually just call it UTP. UFTP on the second line means the sheath is unshielded while the individual pairs inside are foil wrapped. FUTP on the third line is the other way around. The individual pairs are unshielded, but there's foil around the outside of the cable. There's also cables with braiding and foils who offer even greater shielding, such as SUTP, SFUTP, FFTP and SFTP. Cat7 and up is always a shielded foil wrapped twisted pair cable due to the higher frequencies that they're supposed to support. Now for a few examples of some screened cables. Here we have some Cat5e FUTP cable. We can see here that the pairs inside have no shielding, we only have the foil around the outside of all four pairs. Here's some Cat5e SFUTP, meaning it has braiding and foil around the outside of all four pairs. You can see some of the braiding poking out of the sheath there. Cat6 UUTP, notice we have tighter twists than Cat5e, and we also have a plastic spacer in the centre, making it noticeably thicker than Cat5e. Cat6a UUTP looks very similar to Cat6 but is a noticeably thicker cable, about as thick as my pinky finger, with a larger plastic spacer inside. Cat6a SFTP. Each pair is individually wrapped in foil, and we also have an exterior braided screen around the whole lot. The extra screening means that the twists don't need to be as tight, which makes it a bit thinner than Cat6 UUTP. Cat7 SFTP. This looks exactly the same inside and out as Cat6a SFTP that we just saw, but there is a performance difference, so there's other factors involved that we can't see. DINTEK have a wide range of jacks, plugs and fittings to complement each category of cable. Here we have a bunch of shielded and unshielded jacks and plugs. The faceplates pictured on the right are DINTEK's curver plate style, which come in either 1 or 2 gang versions. There's also 1 to 6 gang plates available in the standard US style, much like the Clipsal 2000 series. And DINTEK jacks are a standard size with standard clips, so will fit into other brands of faceplates, even HPM and Clipsal plates with the addition of a bezel or adapter, pictured on the bottom right. DINTEK also have a wide range of patch and management panels, including shielded patch panels and cassette patch panels for Cat6a and Cat7. And of course cables and patch leads, which come in different colours with different lengths, with either a PVC or an LSZH cable jacket. LSZH stands for Low Smoke Zero Halogen, which means it emits limited smoke and no toxic fumes when exposed to high sources of heat or fire. One thing you don't want in a fire is a cable that acts like a wick and transfers the fire into other areas, or takes people out with poisonous fumes as it burns. PVC is slightly cheaper and more flexible, but if it's going into a populated building or an enclosed area where people can't always evacuate quickly, it's better to run with LSZH cable. Building codes in many areas might also require it. PE, polyethylene, is another type of cable jacket. It's more weather resistant and UV protected, so better suited to outdoors or oily or corrosive environments in factories and other industrial settings. One of DINTEK's standout innovations is the Passthrough Easy Plug. In webinar 1 I showed it in action. Here's a video comparing terminating Passthrough Easy Plugs to standard RJ45 plugs. One of DINTEK's innovations is the Passthrough Easy Plug. Now the first time I saw one of these I thought it was a bit strange, but now having used them I've decided they're actually a very neat idea. Instead of butting the wires up inside a standard plug, which takes a bit of skill to get right, I can just push the wires all the way through the plug and out the other side. It seems easier, right? But is it faster? Let's find out. Okay, first I'm going to terminate a standard plug. Slip the boot on and strip off some of the cable sheath as usual. Cut out the cord in the central spacer. I'm using DINTEK's Cat6 solid core cable here, which has thick 23 AWG wires, so it's a bit tougher to work with than the Cat5e cable that I'm more used to. Separate and untwist the pairs. The trick to getting the connector on easily is getting the wires as straight as possible. The easiest way to do that is with a screwdriver or with the back of another tool. Get the wires in the right order. I'm using the T568A standard here, which is the standard we use here in Australia. Next, hold them up to the plug to work out the length we need to cut them. Then push the wires in and check carefully that they've gone all the way home. Push the boot into place. Crimp and done. Now we'll try a pass-through plug using the same Cat6 solid core cable. Exactly the same procedure so far, except I don't want to be as thrifty with how much sheath I strip off. The excess wires are going to be cut off anyway, and a bit of extra length will make them easy to get into the plug. Separate and untwist the pairs. Straighten them out using a screwdriver or with the handle of a tool up against your thumb. Sort the wires into the T568A standard. Give the end a trim so all the wires are even. Now push them through the connector. Now you can also check to make sure all of the wires went all the way through and that they're still all in the right order. Notice to get the connector all the way into the crimper, the clip on the boot needs to be bent up. And crimp and done. Okay, so speed-wise it's a bit faster as it turns out, but using either plug will get faster with more experience, so that speed difference might become more negligible in time. However, when we're talking about time, we also need to factor in not just the time it takes to fit a plug, but also the accuracy. How many times will we get a standard plug wrong versus how many times we might muck up a pass-through plug? With a standard plug, you're going to get a few wrong from time to time. A wire won't have gone all the way in, or a couple of wires might switch places while you're pushing them in, and finding a fault, tracking it down, and fixing it at the end of a job takes up a lot more time than it does to fit a plug in the first place. With a pass-through easy plug, you can easily see all the wires to check that they've all gone into the right places, and that they're all the way in before you crimp. it's going to be very difficult to get one of these wrong, and that's where you're really going to save time. Getting it right first time every time is where these shine. As an example, I had a few test runs prior to filming, and it turned out that all of my standard connectors were duds. Sure, I'm a bit rusty and I haven't done much with solid core UTP before, but I've got eyes and all of these looked fine to me, so I was surprised that they turned out to be duds. However, I knew that my standard connectors were the most likely problem, so I cut those off and put pass-through plugs on instead, and it's perfect first time. Another aspect I noticed afterwards with the pass-through plugs is that I'm getting the cable much further into the plug, so my twists are up much closer to the contacts. That's a performance advantage, and I did that quite naturally without even realising I was doing it. Also, with both types of connectors, I've used DINTEK's Easy Lock boots. Once the locking tab is pushed in, there's no way to push the clip in to remove the plug accidentally. When you do need to remove the plug though, the locking tab is easy to grab and slide out again. Okay, so a very interesting product which is not only easier to use, but more accurate, which is going to be a huge time saver. Another very groovy tool by DINTEK is the Easy Tool 90 for Cat6 horizontal type Easy Jacks. It basically punches down and trims all 8 wires at once, which is much quicker and easier than punching them all down individually, especially when you consider you might be doing dozens of these at a time when terminating patch panels and wall plates. You can see it in action in Webinar 1 as well. There's also a version available for vertical keystone jacks called the Easy Tool 180. You might use vertical jacks where you don't have a big enough wall cavity to fit the wall plate into place without exceeding the bend radius of the cable, or it might just look neater on the type of patch panel you're using. Some people just prefer them for no particular reason. So that wraps up our webinar series. For more information about DINTEK products, please visit our website at www.dintek.com.au, or you can send us an email at sales@dintek.com.au. Don't forget to like and follow us on social media. You can find us on Facebook, YouTube and Twitter under the DINTEK Australia name. Thanks and bye for now.